All right, party people, 9.7, this is where we get electric. So we are talking about galvanic, also called voltaic cells, and electrolytic cells. So these are two kinds of electrochemical cells, and the main distinction we're going to make between these is actually how thermodynamically favorable they are. So galvanic cells are favorable, which I'm just going to call TF for now, which means delta G will be negative, right? We know that from our previous studies that a negative delta G means it is thermodynamically favorable. On the converse, an electrolytic cell is not thermodynamically favorable, so not TF, and that means the delta G for that reaction, that electrochemical cell, is going to be positive. So we'll learn a lot more about these in a little bit, but first we need to do a little bit of background because electrochemical cells really depend on something we learned way back in Unit 4, which was everyone's favorite, redox. Yeah, so reduction and oxidation reactions. When we do electrochemistry, we're looking at electricity, obviously, and that's the flow of electrons. So when we have an electrochemical cell, some reactions or some substances are losing electrons, some substances are gaining electrons. That's what happens in a redox reaction, and that gain and loss of electrons is a flow of electricity, basically, when we set up the cell correctly. So, down here I have some examples of, different redox reactions, but really the main kind we looked at when we studied redox was this sort of thing. And these are called half reactions, right? Where I'm just looking at one substance, like the magnesium, that's losing electrons and therefore oxidizing, or this copper 2 plus that is gaining electrons and therefore reducing. Now, when we talk about reducing, we're talking about the oxidation number of the metal. When we talk about oxidizing, the oxidation number is going up. And if you don't recall, what are those little mnemonics? Leo the lion goes grr. So losing electrons is oxidizing, and gaining electrons is reducing, right? You gain a negative, you get lower oxidation state. So again, these redox half reactions. Also, I'll just note, if at any point you are getting flummoxed in this lecture, just pause it, read the words that are on the slides, maybe rewind a little bit because there's a lot in here. So when we look at these half reactions, we're splitting up two different components of an electrochemical cell, and we're looking at one half that oxidizes and the other half that is reducing. So something that we did in Unit 4 was we looked at something like this, an overall reaction, and we split it up into two halves, right? What is the iron doing to turn from a 2 plus to a 3 plus, and how many electrons have to be exchanged there? Whereas how is the dichromate polyatomic turning into a chromium 3 plus, right? And this isn't like a complete question. There's not electrons shown for the reduction, but you get the idea. So again, when we combine a reduction and an oxidation half reaction, we get this flow of electrons that can allow us to see the flow of electricity. Now, when we are looking at these half reactions, we look at them as reduction reactions. And this is a pretty typical kind of chart for a lot of reduction reactions. And again, these are half reactions. So, just for sake of example, something like fluorine up here, neutral fluorine reduces to fluorine minus, but we also have positive lithium plus reducing to a neutral lithium. Now, what we are learning now that is new is this thing called the reduction potential, and that's this right-hand column that's measured in volts. So capital V is the unit for that. And this basically says how much this reaction wants to proceed. Another way to think of it is it's related to delta G, right? Related to, or you could say, proportional to delta G. But it's a little bit different because here, if something is very likely to react, it has a positive potential voltage. Whereas if it's unlikely to react, we have a lower negative potential. So related to delta G, but the signs are flipped. So that means a negative delta G is going to be a positive E cell, and vice versa. So just to make that explicit, if delta G is negative, that means the E cell would be a positive value, and vice versa. Delta G was positive, we would have a negative E cell. And just as a reminder, that little circle there just means at standard conditions, so 298 Kelvin, 1 atmosphere of pressure. There's also some other conditions we'll talk about a little bit. Now, one of the things we'll be doing, like we have done in previous units, is kind of manipulating equations, right? Like I can flip it around, I can multiply by coefficients. We will be doing that flipping a lot when we talk about redox reactions in electrochemical cells. So this one at the top that I have highlighted, right, that's fluorine's reduction reaction. But if I flip it, right, I can turn it into an oxidation reaction. Now note that when I do that, its original E cell, its original reduction potential, switches to a negative 2.87, okay? So all I've done is just switch the direction. So the reactants are now products are now reactants, and I now have a negative sign, right? And this table makes sense. This note down here, I'm just sort of identifying that fluorine loves making a negative ion. Lithium really likes being a positive ion. It doesn't want to go back to being neutral. So we can see its really negative reduction potential saying lithium does not want to turn back into a neutral atom. It wants to stay, a positive cation. Now, with the manipulations, if we flip them, we flip the sign of our reduction potential. But what we don't do is change the quantity of E cell if we are multiplying by a coefficient. Okay, so I've sort of got this box down here. I've multiplied the coefficient of lithium's reduction reaction after flipping it to make it an oxidation reaction. And even though I multiplied it by 2, notice that all I've done to its E cell was flip the sign, right? It was originally negative, so when I flipped it around to make it oxidation, I made it a positive E cell, but I did not multiply the value by 2. So we do not multiply by coefficients. Now, I am sort of skimming over some of the text on this. When we're looking at making an electrochemical cell, typically we are looking for something that is thermodynamically favorable. Again, another word for this is galvanic or voltaic cell. That means we want an overall positive reduction potential. Now, when we combine two half reactions, we just add their E cells, and we want to make sure that the number of electrons is going to cancel out on either side. So if, for example, I said, hey, I want copper to be reducing in this cell, what other reaction can I find to work with that? Well, again, flipping lithium's reaction, multiplying it by 2, my electrons cancel out, and now I have this positive 3.04 to add to this 0.34 that copper originally had. And let's see, where is the copper 2+? It's this guy right here. Yeah, so we can see that with that 0.34. When we combine the two to get the overall E cell, we're just going to be adding those. So it would be 3.34 volts. Okay. And again, I already kind of mentioned this stuff, but when we multiply by coefficients, we do not change the reduction potential of that half reaction. And I also said 3.4, but my next slide told me it was 3.8 because I can't do math. Wow, I'm already at 9 minutes in. Okay, guys, I'm going to try to pick this up. I am not going to recap how to do oxidation numbers, but you can read that and remind yourself. All the stuff we did in Unit 4. Okay, so what actually is an electrochemical cell? Again, these galvanic cells are ones that are thermodynamically favorable. So we've got a negative delta G. And the key things are we've got our half reactions in separate containers, usually represented as beakers. There's going to be some wire or some other sort of throughway where electrons can travel. That's going to be the flow of electricity. And we also need to have ions that can move between the chambers. So not actually the ions of the reaction, but sort of separate ions from the reaction. And they're there to maintain a charge balance. And this is something we call a salt bridge, which we'll understand more when we look at this diagram. So at first glance, these diagrams are really overwhelming. I know that, but I promise as you pick out the pieces, they will become a little bit less so. So we've got two things happening here in our reaction. We're just gonna kind of pick apart this overall reaction. We've got a solid silver that is oxidizing into a positive silver. I know it's oxidizing because it had to lose an electron, right, to become more positive. So silver oxidizes into Ag+. And then we've got this gold ion, that's the Au, and that is reducing Au3+, and note again with aqueous, or with the ions, they're always going to be aqueous. The gold ion is reducing into gold solid, right? And we also see some coefficients here. That's just to recognize the numbers of electrons being equal. So what do we have on our actual diagram? Well, we have an electrode. That's the anode or the cathode. The electrode is just a metal bar that is going to be that solid metal, right? So AgS, it's a solid piece of silver. Over here, we've got a solid piece of gold. Great. Now we'll see that the silver is noted as the anode and the gold is noted as the cathode. So the cathode is where reduction happens and the anode is where oxidation happens. So as this reaction proceeds, the silver in the anode is basically dissolving to turn into Ag+ ions. So as this cell operates, we're getting more and more Ag+ ions in here, more and more Ag+ ions. And we're also getting more and more of these gold ions, it's kind of cut off here, turning into solid gold. So we're getting more and more gold solid, more and more gold solid building up, and we would actually see a sort of accretion of this electrode on the gold side getting bigger, right? We would actually be able to see more metal being plated on the outside of it. Okay, so that's what's happening here. Let's see what else to note. We've got this flow of electrons noted at this wire connecting the two electrodes. So what is the half reaction happening at the anode? Again, solid silver is dissolving into the solution in the beaker. And as it does that, it has to lose an electron. Where is that electron going? It's going over here to meet the gold, right? Because the gold ions are reducing. So they need some electrons in order to help them reduce their charge, okay? So the electrons are flowing from the anode to the cathode. And we've also got the overall potential of this cell right here in the middle. This is a pretty common notation. So positive 0.70 volts. This would be the E cell for this electrochemical reaction. And then other things to note, I think, is really just the salt bridge. So again, this little archway in the middle is our salt bridge. And we can see that it says right here, you've got potassium and nitrate ions. And you see that they're not just going in any direction, but the nitrate ions are going towards the silver side. And the potassium ions are going towards the gold side. And just think about what's being produced or being used up in either beaker, that this salt bridge is there to balance out. Okay, so on the silver side, we're making more positive charge in this beaker. We don't want the positive charge to get out of control, so we send some negative charge down through the form of the nitrate. And that will balance out the Ag pluses over here. Alternatively, what's happening on the gold side, the reduction? Well, we're losing all of this positive charge, right? This beaker of the gold started really positive. And as this reaction proceeds, we use up all that positive charge. So we're going to replenish that rather, with some more positive ions in the form of this potassium. So these ions are free to move freely, they're free to move freely between each side, the potassium and nitrate, but they're going to move to the side that's sort of got a charge deficit that they can help fix. And that's a galvanic cell. Amazing. There is a really great 9-minute Khan Academy video of someone basically diagramming this whole thing. I'm not gonna make you watch that now, but you can snag the QR code in your slides. And I recommend diagramming that on this blank one if you want. So I mentioned the terms anode and cathode. A nice mnemonic is anox and red cat. I don't know why I wrote the word fat there. Fat red cat. Anyways, the anode is where oxidation takes place. The cathode is where reduction takes place. Anox and a red cat. So one thing I didn't really emphasize is that the mass of the electrode, well, I did mention, for the cathode, the mass of that cathode electrode is increasing, right? That is the red sort of blob here. The mass of solid gold is increasing, whereas the mass of the solid silver is slowly decreasing. And we'll see this side maybe start to shrivel up and look wimpier, right? So this mass is going to decrease. The silver solid mass is going to decrease. And the solid gold mass, that cathode, is going to increase. Now, you might wonder, Spencer, how am I going to remember all this? Like, there's so much stuff. Look at the overall reaction. What the heck is happening here? Solid silver is getting used up. Should the mass of solid silver go down? It's a reactant. As the reaction proceeds, you bet it will. Alternatively, solid gold is a product. Should the mass of solid gold go up as the reaction proceeds? Yeah, you betcha. You're going to make more product, right? So I know there's a lot of components here, but if you are able to split an overall reaction into its half reactions, sort of identify what's gaining electrons, what's losing electrons, what's turning into a solid versus what's turning out of a solid, you can figure out a lot of questions about electrochemical cells. Okay, I'm going to skim through some of this stuff about electrolytic cells because I want to do some proper practice. But yeah, I've already said that. Okay. All right, here's a good one. So we are given two half reactions, and we're told we've got solid copper, solid zinc, solution of copper ions, solution of zinc ions, salt bridge of potassium nitrate. Great. We are given two half reactions for the copper and the zinc, and we're asked to make a galvanic cell using these two half reactions. Our first question is to write the net ionic equation for what reaction is actually taking place. So before we are able to do that, we need to remind ourselves, if we're told it's galvanic, that means E cell is positive. It's a greater than 0 value, right? The other thing we need to know is that one reaction must be oxidizing. So right now, both of them are reduction, which means I have to flip one of these two reactions. And which one should I flip so that when I sum the two reactions, I'm going to get a positive E cell? Well, if I flip this one, right, the copper, I'm going to get a negative 0.3 plus a negative 0.7. Two negatives adding together, it's going to be another negative. So that's not the one. But if I flip this guy, which already has a negative potential, its new potential will be plus 0.76. And when I'm adding this 0.34 with the newly flipped zinc's half reaction, I'm going to get an overall positive, right? Positive E cell, that means galvanic, that's good. So I'm going to flip this guy, and therefore flip its reduction potential. And then I don't need to add anything or multiply by anything because the electron count is still going to be equivalent. So it's going to look like that copper 2 plus its 2 electrons, turning into copper solid. And I'm just skipping some of my aqueous signs for time. The zinc solid is now the lone reactant for the second reaction, turning into zinc 2 plus and the 2 electrons, right? So our 2 electrons cancel out. And what we're left with when we add these up is we've got the aqueous copper on the left and that solid zinc on the left. That's turning into the aqueous zinc and the solid copper on the right. Okay. Now we're also told to calculate the value of E cell. So that's going to be these two values added together, 0.34 and 0.76. Just going to add them up, and that's our overall potential. So that's going to be 1.10 volts. Awesome. And that's a positive value. Now, before we move on a little bit, I did want, let me just scan what else do I have in here. So, yeah, okay. Give me 5 more minutes of your time. I'm really appreciative, guys. If we look at this overall reaction right here, this guy right here, we just made this beautiful electrochemical reaction. We know which thing reduced, right? The copper we didn't change from its reduction reaction. So the solid copper electrode, is that the cathode or the anode? What do you think? It's the cathode. Remember, the red cat. So this guy is our cathode, which means there's only one other option. The zinc is our anode. Remember, anox, red cat. So zinc is oxidizing because its charge is going up. So we can even write those phrases out, right? Like zinc is oxidizing and the copper reduces. Sometimes that's helpful just to like really get in the habit of, making these claims using this vocabulary so that when you see it all jumbled together in a complicated problem, you know what these things mean. Okay, now how about this one? Where is the flow of electrons going? Is it going this way? Is it going this way? How do we know? Well, let's look at our reaction before we combined them, right? Looking at this guy. Which thing is producing the electrons? It's the copper, right? Or no, I'm sorry, it's the zinc, right? The zinc, as it is oxidizing, right, it makes these 2 electrons, which the copper ions just gobble up. They're like, nom, 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 negative electrons. So the zinc, the solid zinc, is the producer of electrons. Okay, so as zinc oxidizes, it produces electrons, which means that the electrons are flowing from the zinc, right? This is the flow of our electrons. Got our little E's. And why are they going towards the copper? Well, because the copper is reducing. In order to reduce your charge, you need some negative electrons, right? Okay. Up here, we would write our positive 0.1 or 1.10 volts, our overall E cell. And then the last thing, well, 2 last things we can talk about. One is which of these electrodes, the cathode or the anode, is going to be increasing in mass. Pause the video for a second. Which of the electrodes will increase in mass as the reaction occurs? Well, again, we can look at our overall reaction. Which thing is turning into a solid product? The copper is making solid, right? So we're going to see more and more copper kind of building up. And we're also going to see less and less of our solid zinc. We're going to see this guy sort of shriveling and maybe getting, sort of rusty looking as it deteriorates. So zinc mass is going to go down and the copper mass is going to go up. Zinc mass goes down and copper mass goes up. And you can also, sort of start to identify these patterns already between anode and cathode. But it's always best to lean on the reaction, the given information. And where would the potassium and nitrate go? Well, the copper is getting rid of a positive charge as the reaction proceeds. So we're going to need to send some positive charge towards the copper side. The zinc is producing a positive charge as the reaction proceeds. So we're going to need to balance that out by sending some negative charge the zinc solution's way. Ooh, doggy. That's a lot. Okay. I haven't really talked about electrolytic cells, but again, these are just thermodynamically unfavorable reactions, which means delta G is positive, and it means that E cell is negative. E cell is less than 1, or sorry, less than 0. Now, the question here, how much electricity is required for this reaction to occur? So we're given a solid gold and an aqueous silver. Okay, so if solid gold is a reactant, that means this guy has to be flipped. And if the aqueous silver is the reactant, that means this guy has to be flipped. Oh, buddy. So if both of these get flipped, this now turns to negative 1.50. This now turns into positive 0.80. So the overall electrochemical potential of this would be, or sorry, I miswrote that. It's just 1.50. Would be negative 0.70 volts. Again, it's just adding. It's nothing too bad. There's another video here on electrolytic and sort of identifying these. One thing I will say is to drive an electrolytic cell, you have to add external energy. So this would be like I'm hooking a battery up to this reaction. And you can kind of see that in the still here where it says power source. You actually have to hook up an external battery of some kind that drives this reaction. So instead of that overall voltage, you'll see a power source usually at the middle. But otherwise, an electrolytic cell is going to have the same sort of layout where you've got a cathode and an anode and a flow of electrons and all that jazz.